Here is what we're going to do. I need Q radiation C. I have one equation for it, equation 3, the ghost of which is still seen here. I need Q radiation C in terms of some known quantity. So the first thing I'm going to do is, instead of JC, I'm going to write everything in terms of Q radiation C. So from equation 4, look at this. JC is the following. It is sigma Tc to the power 4 minus Rc Q radiation C. I'll rewrite it here. So from equation 4, Jc is sigma Tc to the power 4 minus Rc Q radiation C. Does this make sense to everybody? I'm just rearranging it and writing Jc. Why am I doing that? Is because from equation 5, wherever I have a Jc, I can substitute in terms of Q radiation C. So I'm going to do the substitution. This, let's call this as equation 6. Equation 6 substituted into equation 5. And you can see this gets out of hand very, very quickly. Okay? So equation 6 substituted into equation 5. We'll have to write it out here. So Q radiation C is, instead of Jc, I have all of this. Sigma Tc to the power 4 minus Rc Q radiation C minus sigma T wall to the power 4 by RCW plus, bear with me, I'm going to substitute one more time for Jc. This is sigma Tc to the power 4 Rc Q radiation C T ice to the power 4 by RIC. So we have a couple more minutes left. Is everybody seeing the basic idea of what we are doing here? Essentially manipulating a lot of things. Okay, we focused on the sealing because that's where our area of interest is. On the sealing, there is conduction heat transfer, there is convection heat transfer, there is radiation heat transfer between the sealing and the enclosure, which is the wall, and the ice. All of that culprit is this guy Q radiation C, which comes from this network that we have drawn here. So, what you will see is that if I take this equation, I will have to calculate this 2 times because of the fact that the emissivity of the sealing has 2 values. One is 0.05, the other is 0.94. So I'm going to get 2 iterations of this particular equation. I'll write down the steps and then we'll come back and finish it off. I'll post the entire solutions as well for you to see if you'd like. Couple more minutes and I'll leave you for the day. We still have the semester to finish. So each epsilon C, let me call this as equation 7, we're running out of numbers too. Equation 7 is calculated, and I'll write that down and we'll be done with it. Q radiation C for epsilon C of 0.05, Q radiation C ends up being the following. Is 98 times sigma Tc to the power 4 minus 325. So it becomes really simple. All I'm doing is taking all of the terms containing Q radiation C, combining them together and writing everything in terms of Tc. And for epsilon C of 0.94, Q radiation C becomes 1846 Tc to the power 4 minus 325. Once again, that's the same thing. And then I have equation 3, very last step. Which is Q radiation C 9817 288 minus Tc minus 224. This is the same as before. Tc minus 273 minus 5. So this was equation 3. All I have to do is equate these two. Solve for Tc to get Tc for this shiny panel coating. Equate these two to get a different Tc for the brown coating. Whichever is going to be lesser than 9.4 degrees is out of the game. Okay, so if I write it out, obtain Tc by equating equations 3 and the second of this lot. So Tc for the brown coating, solving this, Tc for the shiny coating. The shiny coating will give you a higher temperature because there is lesser heat removed from radiation. Which is why if you go to an ice rink, the top surface is typically shiny. Okay, so this is the temperature that we need because we need our temperature to be greater than 9.4 degrees Celsius. So I went over the last few steps a little faster. Okay, I'm going to post the problem in its entirety with all the steps outlined. Please take a look at it. It is a surefire question of this nature for your final exam. Okay, thank you.